Hello everyone, we are team 1074 and are tutored by Dr. Thomas Dunn. Today we are going to share a model about how multi-species mixed groups can collaboratively monitor predators. This issue is of great significance in nature. In multi-species mixed populations, individuals of different species will jointly monitor predators through their own alert behaviors to enhance overall safety. The objective of this project is to construct a mathematical model that describes the probability of a predator discovery for the entire population over time. We start from the simplest assumption, that is, each individual is independently detected, and then gradually introduce mechanisms. To simplify the model and facilitate derivation, we make the following assumptions. And to ensure the clarity and ease of use of model, we have defined some symbols and settings, which are respectively used for aspects such as group structure, time, individual detection ability, and dynamic propagation.
Let's start with the simplest model first. That is, each individual independently detects predators. In this model, we assume that each individual of the species has an independent detection probability of Pi. Then the probability P not detect of the entire group not detecting predators at a certain moment is the product of the probabilities of all individuals failing to detect. We introduced the time dimension. We no longer simply discuss whether a predator was found, but turn to the time when the first discovery occurred. Here we transform the detection process of each individual into the continuous random process, which can be described by an exponential distribution. The probability P detect of the group as the whole discovering predator is the product of the probabilities of all species not being discovered, which is P detect T equals to 1 minus the product of e to the negative lambda I nit equals to 1 minus e to the negative at, and we set A equals to sigma of lambda I ni. So if we assume that there is no propagation effect at a certain moment, that is, there is no information transmission among groups, then in this case, the module will degenerate into the simple individual detection model. The differential equation at its time is du over dt equals to negative au, and it can be easily solved to the result p detect t equals to 1 minus e to the negative at. When an individual detects a predator, it will increase detection probability of other individuals. This alert spread effect is dynamic, so our module also needs to be adjusted accordingly. So if we extend the original differential equation to du over dt equals to negative au minus alpha u times 1 minus u. The left of the equation du over dt is the rate of exchange of the proportion of the undiscovered, and for the right first item au, it represents the rate at which an individual independently discovered predators. The second item, alpha u times 1 minus u, represents the interaction between the undiscovered individuals and the discovered individuals within the group.
Okay, next let me introduce our result analysis. First of all, here we consider A and alpha as constants. That is, they are independent of K. Here we can organize the model as the u prime t equal to negative A plus alpha ut plus alpha u squared t. This is a Bologna differential equation, so we can solve it directly to the solution ut equal to u0 times alpha plus A over u0 alpha plus A minus u0 alpha multiple e to the A plus alpha t. Then we can draw the graph of detection probability relative to time here by setting the values of some parameters like A equal to 0.1, alpha equal to 0.3, u0 is 0.95. Here 5% animals were initial alert and delta t is 0.1, total t is 30, and we can draw such pictures. Then we, next page, come to consider the situation where A and alpha are related to K. So we can write down these two expressions. AK here means most species will have more independent sources of clues. and A here is a linear process, while B presents an interactive nonlinear process, and the denominator are the saturation effect. Next page, we come to the part of numerical study. First, we set parameter values to A equal to 0.01, B equal to 0.02, gamma is 0.12, U0 delta t are just the same, and the total t we set to 10 seconds. Then we can, using Euler method, substituting different k values to draw the graphs corresponding to different k values. Here we find as k increases, the function graphs gradually change from linear growth to a stage of first slow growth, then rapid growth, and finally entering slow growth. So we believe that exists a minimum number of spaces for there to be a non-trivial advantage, and also exists an upper bound for the number of spaces in which additional type of animals have a smaller impact. We can also understand the problem at finding the minimum k value where the first order derivative is greater than 0 and the second order derivative is equal to 0. That is the k minimum. And finding the maximum k value where the first order derivative is less than the boundary value. Here we say the boundary value is approximately 0.02, and this value we set is k star. Here we still use the Euler method to find the detection probabilities corresponding to different k values under the condition that total t is 10 and draw such scalar plot. However, since the k value here both are all corresponds to discrete points rather than a continuous image, we use polynomial regression to concatenate these points to form a reasonable continuous image. And through differential equation, the spatial specific value of k minimum and k star can be calculated. You can see as shown in the graph, we use this line to fit all these points and find the k minimum value is approximately equal to the 4.5, and the k star is approximately equal to 18.23. So that's the whole of our model. The following are the possible shortcomings of our model. We might overrate the benefits of mixed groups or overlook the importance of key individuals. We also did not have a way to confirm the absolutely specific and precise growth coefficient. Then predators also have their own unique characteristics, and in reality, one may come into contact with various type of predators multiple times. And in conclusion, willow groups composed of different species are more likely to spot predators. The overall trend is a slow growth at first, then a rapid growth, and eventually a flattering. There exists a minimum number of species that enables the growth rate to achieve a non-trivial advantage, approximately when the number of species fall the biggest integer under 4.5. There is also an upper limit to make the impact of new animal species on the number of species smaller and smaller, which occurs the number of species approximately 19 is the minimum integer over 18.23. So that's all our model and our results. So thank you for listening.